Recently, in the year of 2012, a group of researchers at the Indian Institute of Science, Bangalore proposed a new stable geometry for fracture toughness measurement. They suggest that this new geometry, the so-called clamp beam, has particular advantages at small length scales. By small, they do not mean centimeters or even millimeters for that matter. What they mean is specimen dimensions which are of the order of the thickness of a human hair. Yeah, you guessed it right, a few microns thick. The contemporary interest of the scientific community in quantifying the mechanical properties at micron length scales arises due to miniaturization of devices and has gained momentum due to advances made in the micromachining tools like the microlithography and the focused ion beam milling. The simplicity of micromachining the clamp beam makes it user-friendly in terms of handling and testing. This video showcases the crack stability of clamp beam geometry at macro scale tested in a universal testing machine.
Control crack growth and determination of arc curve behavior in quantification of fracture toughness has been of interest to the fracture community since the last century. Not many geometries exist which have the capability of controlling the crack growth. For example, the 3-point bending leads to catastrophic fracture. This is where the clamp beam geometry finds its real application. One can easily determine the arc curve behavior for this geometry even for the most brittle of the brittle materials. Research on brittle polymers, intermetallics and ceramic materials have all shown positive and promising results. In this video, we will test the clamp beam specimen made from a polymer polymethyl methacrylate, in short PMMA, a linear elastic brittle material. A starter notch of relative crack depth of 0.34, which means for a 10 mm width specimen, you make a notch depth of about 3.4 millimeters with a finite notch root radius, is created by laser cutting of PMMA.
The screen shows the clamp beam specimen with a starter notch being loaded at the center using a wedge-shaped indenter. This is a displacement controlled test with a displacement rate of 0.06 mm per minute. The top right portion shows the recorded load that corresponds to the applied displacement at that instant. Let's just fast forward the loading so that we don't have to wait to see the cool stuff. The crack has now started to grow. Interesting point to note is that the polymer hasn't undergone a rapid crack propagation, which is quite common with brittle materials. In fact, the crack grows incrementally at a constant load. In addition to using this as just another geometry for fracture toughness evaluation, the clamp beam can be used for pre-cracking, arc curve determination, cyclic loading behavior, and many more applications. Hope you liked this video and thanks a lot for watching.